All right, so welcome to class. This is chemistry class, and we're going to be learning all about chemistry. Now, some of you are new, some of you are not new. Some of you have already taken chemistry, and we're going to try to, move at your pace. Hopefully, you know a little bit about chemistry. Why don't you tell us a little bit about yourself?
My name is Fred. I go by Fred. You can call me Fred. I'm interested in, pre-med or something like that.
Pre-med. Okay, that's good. Good stuff.
Yeah, I need this class to get on, but I had chemistry in high school, so I'm not sure that this is going to be a real hard class for me.
Yeah, that's probably right. You're probably right. It probably won't be a very hard class for you, which is great. So, if you already know stuff, you can just let me know, and we can move through stuff faster, right? So if you know something, we can just move right through it. But we're going to start off talking about what we call the scientific method. Now, the scientific method is a cycle. It's a cycle. It has to do with observing, making conclusions. I mean, a conclusion after your first observation is really just a hypothesis. But even after your last observation, it still is a hypothesis because people are always learning new things. So in this example, the person is making a conclusion about the duck and makes a decision that if that duck is a real duck, it will eat bread. And so it feeds some bread to the duck, and then the duck doesn't eat the bread. The duck doesn't eat the bread, and so they have to make a different conclusion based on their new observations. Okay. And it's cyclic in this nature. We have what we call facts. We have laws, scientific laws. Usually a law is an equation that we kind of find based on the relationship between different parameters. We have what's called a hypothesis, right? A hypothesis, and it's nice to generate a hypothesis when you can beforehand. Unfortunately, sometimes after we generate that hypothesis, we feel like we are forced to prove that we're not crazy, that our hypothesis is right, and so we're only trying to figure out if it's right or not, and we're afraid that it's wrong. A theory is usually a collection of ideas or a strongly based understanding of a concept, and we sometimes think of the word theoretical like, oh, it's still kind of tenuous, or nobody knows if it's real or not. But in the case of chemistry, usually theories are very close to laws. Okay, so a lot of observations lead to methods of understanding, and we call these methods models. Okay, and the model is a way for us to teach each other and a way for us to think about a system. But we have to know that it's not right. The model's not right. And that's not a problem. It's not a problem that it's not right, right? We can have a model that's incorrect and still learn a lot from it, all right? We can overuse models, though, sometimes. Sometimes we overuse models. We discover new data and new ideas, but they don't fit in the model. And then we say, well, this can't be right. But it doesn't mean it's not right. Okay? So we always have to think about our models and recognize what they are, and that they are just models. For example, early on, the idea of an atom was a mixture of positive charged particles and negatively charged particles in this sort of a format, which they called a plum pudding format, where there was mostly empty space, but some larger entities. But later on, we identified a different model that made more sense for some of the science that was occurring at the time. And that is this kind of a model. Now, are you familiar with this kind of a model?
Yes.
What do we call this thing in the middle?
That's the nucleus.
That's right, the nucleus. And do you know from your experience what these positively charged things are called?
Those are protons.
That's right.
And the orange things are neutrons.
That's right, protons and neutrons. Now, neutrons, do they have a charge?
No, no charge, no charge.
Okay, now what do you call the things around the outside?
Those are electrons.
Electrons, very good. And do the electrons have a charge?
Yes, they have a charge.
What's their charge?
It's a negative charge.
Okay, that's right, good, negative charge. And the electrons kind of, you could say kind of like a planetary model, they revolve around the nucleus, right? Now this is a model again, and if we tried to kind of make sense of that model, we might have a hard time. Here's a little video that I want to show you about this model. And afterwards, I'm going to ask you, why did they make this video?
You're watching the Nova Science Now video podcast.
Okay, so kind of a silly show there, but why do you think that they actually made that?
I don't know. Maybe they wanted us to know how far away the electrons were from the nucleus?
Yeah, I think that's true. I think another reason that they made it, though, has to do with the model, right? If we had an actual existing model, the correct scale size of an atom in front of us, would that be very helpful?
Probably not, because the electrons are so far away you couldn't see them anyway. So, I guess about the model, they're basically saying that not all models are, well, the way things are don't always make a good model.
That's right. And so even if we had the thing right in front of us, it wouldn't be easy to understand because the electrons would be farther than our eyes could see, right? So sometimes the models that we have don't actually reflect reality, but that doesn't matter. We can still use the models. So we don't just ditch models all the time, and we also don't want to get stuck into models. So if the model doesn't fit some data that we've collected, we have to make sure we understand this is a model and it might fit somewhere. We might have to adjust our model. And we'll do that. We'll do that in this course quite a bit, where we say, so this is what we talked about, but it's actually like this. We use this as kind of a general principle, but we'll give you new rules. So don't get mad at me if I kind of, don't tell the truth all the time. I'm going to give you piece by piece so that we can build upon our understanding of what's going on. An example of a scientific law right here. We have the pressure of a gas compared to the volume of the gas. And this is an interesting little, oops, it doesn't look like that video is working there. But here in this video, you can see a balloon inflating in the presence of a vacuum. Okay, so if you take a balloon, put it in a vacuum, the balloon will inflate because there's this relationship between the volume of the balloon and the pressure. And we'll talk about that in chapter 11 as we move forward. All right, so let's have a little conversation about matter. Matter is our word for anything that has mass. And we say something has mass if you put it on the scale and you see a number, right? So if it's something that's measurable, we say that's what mass is. Now, there is a little bit of a discussion that we have to have about the difference between mass and weight. Now, weight is often what we say, and we sometimes use those interchangeably. It's better to use the term mass in chemistry class, but the real reason for that is it's better to we want to understand, right? The real reason for that is because when you talk about weight, you're referring to the force that you might feel, or the force that Earth's gravity is pulling on that mass. And that number, that value, is called the weight. So, for example, if I have a scale, right, and I stand on this scale. Here I am, I'm standing on the scale. Let's say it weighs, it says I weigh 600 pounds. That says 600, sorry about that. So it says I weigh 600 pounds. Well, how does that work? Well, what's going on here is a spring, and as we stand on it, the gravity pushes down on that spring, and how the amount of compression that the spring undergoes, that is an indication to the scale of how much we weigh. Okay, so what happens if we go to the moon then? Do you happen to know anything about the gravity on the moon?
Yes, I do.
What do you know about it?
It's less.
That's right, it is. There is less gravity on the moon. Do you know how much less?
I think I remember it's like 1/6.
That's right, 1/6. So if you weigh 600 pounds, if your weight is 600 pounds on the moon, on the Earth, here's Earth, right? Then when you go to the moon, your weight will only be 100 pounds, okay? Because the gravity will pull you down less, only 1/6 the amount on the moon, all right? So, do you lose weight when you go to the moon? People think of losing weight as not being so fat, right? You're not going to lose that kind of weight, but you will weigh less on the moon. Now let's do another scenario. Here's my Earth, and here's the moon, smaller, right? So if I'm on Earth and I stand on what we call a balance, okay? If I stand on the balance, and now I'm going to put my 600-pound mass here, and I'm going to stand right here to to balance that lever there, that fulcrum, or that balance, right? I want to balance it. And then I take the same balance and put it onto the moon. Now, when I stand here on the moon, what kind of a balance are you going to need on the moon?
You're going to need the same thing, because even though you're on the moon and there's less gravity, you still need to balance it. So you're going to have less mass, or you're going to have the same mass on the moon, so you're going to need the same mass on both sides.
That's right, that's right. So here I can use this arrow to represent the force. Use that arrow to represent the force. And then here we have less of a force, but there's going to be less of a force felt here as well, so I'm still going to need the 600 pounds. Okay, very good. So there is a difference between mass and weight, and we want to use the term mass in this class more frequently, although sometimes we'll slip and we'll use weight, and it's not that big of a deal, but we want to know the difference. All right, there's some other terms that we want to know. An atom, and you probably are familiar with the term atom, right? What do you think of when I say atom?
Like we said, the proton, the neutron, the nucleus, and the electrons around the outside.
That's right, that's right. So this is our model of the atom. And, here's a nice, that one's having trouble too. So this is the model of our atom, and that serves us very well. It's not exactly correct. There's a lot of problems with it. We'll even try to fix some of those problems in this class as we go. But that is our fine model or fine understanding for the word atom. Now, molecule. A molecule is a combination of different kinds of atoms, or sometimes just the same kind of atom, together into one unit, to one piece or one part. And it forms something new, So it has different properties. Water is an example of a molecule. Okay? In water, do you know the chemical formula for water?
Yeah, H2O.
That's right, H2O, right? H2O is the chemical formula for water, and that essentially means 2 hydrogens, H is hydrogen, and 1 oxygen, right? And we could draw a little picture like this, and we'll talk in later chapters how we know what it's supposed to look like when we draw it. But the idea is that water is molecular, or it's a molecule, and this is the unit of the water molecule, right? This is what we call the chemical formula, and this is the unit. All right. Now, element. Element is when you have one kind of an atom. One kind of an atom. So, in an element, we only have, so if something is elemental, we say, we only have one kind of atom. Okay? So, hydrogen can be elemental. Whoops, let me get that out of the way for a second here. Got to bring in what we call our periodic table here and take a look at it. This is our periodic table. This is the list of all of the elements that we have. I'm sure you've seen one of these before, right?
Yeah.
And the different elements that we have here, we can name them. They all say their names right here: hydrogen, helium, neon, argon. I don't care if you memorize this periodic table, but you do need to become familiar with it. So you're going to want to have one handy and be able to look at it all the time. Okay? And I also want to tell you one other thing about the periodic table. See these numbers up here: 1, 2, 3, 4, 5, 6, right? All those numbers. Those numbers tell us how many different protons are in the atoms of those kinds of elements. Okay? So if I have an atom of hydrogen, how many protons does it have? 1. That's right, it has one kind of proton. If I have an atom of boron, how many protons in that atom? 5. That's right, 5, because that's what that 5 is. All right? So that number is the number of protons that are in the atom. Also, it's the number of electrons that are in the atom for an atom that has no charge. So if there's no charge on the atom, that means they have the same number of positives and negatives. So that number can then also be the number of protons. So if I have an atom of oxygen and I say there's no charge on the atom, how many protons does it have?
8.
That's right. And how many electrons? 8. That's right. They both have 8 electrons. Okay? So, all right, so oxygen has 8 protons and 8 electrons. Very good. So, an element differs from another element by the number of protons that it has in its nucleus. Okay, so you are familiar with some different kinds of elements, I'm sure. You've heard of gold, sulfur, carbon, specifically diamond, right? I mean, graphite is another kind of carbon. So we have elements that come in different forms, right? Different ways that elements can combine. But if they're elemental, they're still all the same kind of atom. All right? Now, let's talk a little bit about these chemical symbols. We have letters to help us remember or kind of communicate with each other about the elements that are in a given compound. And these chemical symbols here, carbon, calcium, bromine, don't always follow the English alphabet, right? Because some were named before English was the primary scientific language. But there's always either 1 or 2 letters to help us kind of recognize that kind of element. And we will use those letters when we write our chemical formulas, like water, H2O. That's an example of a chemical formula. And that 2, again, tells us that we have 2 hydrogens and 1 oxygen. Okay? All right. So, now, other words that we want to become familiar with, compound. Now, a compound is, let me draw you kind of a diagram where we think about the different kinds of compounds, okay? So, if I'm going to draw all of my compounds that I have in chemistry, or at least the majority of the ones that we're going to learn about in this class, okay? So, here are all of my compounds. Within all of those different kinds of compounds that I have some that are what we call molecules. And we have another group of compounds that are called ionic compounds. So I have molecules or molecular compounds, and I have ionic compounds. All right? So we'll talk more about what those are. Molecules, we can recognize a molecular compound because it's a compound that is only made of nonmetals. Now, I don't know. Do you know where the nonmetals are on a periodic table?
No, I can't remember that.
Okay, so here's how we can separate the metals from the nonmetals. It's this green staircase. Okay, the green staircase there separates the metals from the nonmetals. And then you can kind of look at some of these, like for this one down here, right? These ones down here. I don't know, have you heard of that element?
Iron?
Yeah, iron, right? So we can remember that iron is what? A metal or a nonmetal?
It's metal.
That's right, it's a metal. So iron is a metal, and that means this side of the staircase, this staircase down here, all of these, all in here, are metals, whereas these ones over here, those are nonmetals.
Okay.
So when a compound only contains nonmetals, then we say that the compound is molecular.
What about hydrogen? I thought hydrogen was a nonmetal.
Oh yeah, you're right, you're right. Hydrogen is a nonmetal. So it is an exception to our little staircase really. Or you could think of kind of the staircase tipping over like that, I don't know. But you're right. Nonmetals are all over to the left here, or sorry, right here of the staircase, or hydrogen. Hydrogen is also a nonmetal. So compounds that can contain only nonmetals are molecular. Okay? So molecules we can recognize because they only contain nonmetals. All right? So that's nice. Ionic compounds will, the definition of an ionic compound is it contains ions. But that's not a real good definition for now because we don't know what ions are yet, and we're not going to talk about them until next chapter. So for now, we're going to be able to recognize an ionic compound because it has a metal and a nonmetal. All right? A metal and a nonmetal. And you know some ionic compounds. So, I mean, well, most people can recognize this compound when they see it. I don't know. Have you ever heard of that compound before?
Yeah, I know that compound.
What's it called?
Sodium chloride. It's salt. It's what's in the salt shakers when you eat.
Okay, sodium chloride. That's right. Now, in chemistry, we have a little bit different definition for the term salt. So, and we'll introduce that definition later on. And, well, I can tell it to you right now. Anything that is an ionic compound is a salt.
Not just sodium chloride?
No. Anything that's an ionic compound is a salt. And in fact, in that salt shaker, you have other salts or other ionic compounds as well. And you also have some kind of molecular compounds. So there's other stuff in your salt that you put on the table. It's not just sodium chloride. And sodium chloride is not the only salt in the chemistry classroom. Okay? So, compounds, any combination of elements, whether it's molecular or ionic, are compounds. Okay? All right. Now, we want to also introduce this idea of a chemical reaction. Chemical reaction. You've probably seen this in your chemistry classes before, where chemistry occurs, right? You start off with a compound, and now the compound is interacting differently with each other. So like for this case, we're kind of separating the hydrogen and the chlorine from each other into ions, actually. Right? And we'll talk more about what ions mean later. But ions are charged atoms. So, whereas a physical reaction, we just take the same compound and there's no change in the chemistry, right? We went from L to S. Do you know what this L business means?
Yes, it's liquid. L means liquid.
That's right. And S?
Solid. Solid. S means solid.
That's right. So, liquid to solid, what is that called where you take the liquid to solid?
Melting.
Melting. Liquid to solid. Are you sure?
Oh, no, freezing. Freezing. Sorry about that. Freezing.
That's right. Liquid to solid is freezing. And when you freeze something, you're not changing the chemical formula. See how the chemical formula is not changing? It's still 2 hydrogens and 2 oxygen. Therefore, we call that a physical reaction.
Okay.
All right, so we have chemical reactions and physical reactions, and we want to become aware of them because sometimes people get confused about what the difference is, and they begin to think that when there's a physical change, it's actually some sort of a chemical change. Now, you're already a little bit familiar with some chemical formulas. You knew about sodium chloride. You knew about water, H2O. These are some other chemical formulas, and we're going to introduce lots to you, right? And the things we need to recognize when we see these chemical formulas is we need to recognize the different kind of elements that there are, So here we have hydrogen and oxygen. Over here, can you tell what kind of different elements there are?
Yeah, there's two different kinds. There's iron and there's PO.
Okay, well, PO, see how this O is a capital letter? Well, that means,
No, sorry. It's not PO. P is where's the periodic table?
there we go.
P is phosphorus and O is oxygen. So there's three different kinds. Iron, phosphorus, and oxygen.
Very good. That's right. That's right. So we can look at our elements and we can know what the different kinds of elements that there are in there. And then these numbers down below, they also tell us how many of the different elements there are in that compound. So if I have this compound, FePO4, we need to be able to know how many irons.
Just one.
That's right, one iron. How many phosphorus? How many phosphorus are there?
One.
That's right, one phosphorus. And how many oxygen?
The 4 means 4. 4 means 4 oxygen.
That's right. 4 is for the oxygen. There's no one or no one for the iron, no one for the phosphorus, right? But you don't need that because just like in the oxygen here, if there's nothing, we just assume it's a 1. So, can you tell me how many sulfurs are in H2SO4?
One sulfur for every H2SO4.
That's right. Very good. How many different kinds of atoms are there?
3 different kinds of atoms: hydrogen, sulfur, and oxygen.
Very good. Excellent. All right. Now, we also have scenarios where we talk about just 3 elements, like hydrogen, oxygen, nitrogen, fluorine, iodine, and bromine. These 3 elements, when they're alone, elemental, we call it, right? When they're all just by themselves, they go around in pairs. And so we say that they are diatomic molecules, or they are molecular, okay? So because there's more than one atom, it becomes a molecule, and now that we have, even though they're elemental, there's more than one atom, sorry, so it's a molecule. And these atoms, these elements are molecular in nature, right? In nature, you'll always find them as pairs like this, okay? And that happens with a few other examples, but in general, the thing that we're going to remember is that some of these atoms, some of these elements are diatomic or molecular. Do you know what diatomic means?
Yeah, 2 atoms. 2. Di means 2.
That's right, diatomic. All right, now, chemical formulas allow us to see the different kinds of elements.
Iron and oxygen.
What's that?
Iron and oxygen.
Oh yeah, right here. That's right, there's iron and oxygen in that compound. That's right. Do you know if this is a molecular compound or an ionic compound?
I can't remember what the difference is.
Okay, so let's see if we can look at our chart here.
Ionic compound.
What?
Ionic compound.
Oh, iron oxide? That's right. Iron oxide is an ionic compound. How did you know?
Because ionic contains metals and nonmetals, and iron is a metal.
That's right. Now, if you didn't know that iron was a metal, you could always use your periodic table and see that it's to the left of the staircase. So that's a periodic, that's an ionic compound. Sometimes chemical formulas can be written different ways, all right? Like these 2 examples here for this compound. This compound here is called, well, it has a common name, urea. Not all compounds have common names. Water is an example of a compound that has a common name. Urea, ammonia. You might have heard of ammonia before. You know what the chemical formula for ammonia is?
No, I don't know that.
Okay, yeah, you don't need to know that, but these are chemicals that have common names, okay? And we'll want to become familiar with the ones that are important, okay? But what we want to pay attention to here is that chemical formulas, you can have multiple chemical formulas for the given same compound, all right? Sometimes chemical formulas will be written a certain way, though, because they want to help you understand the structure. So, for example, this is what the chemical structure looks like in ball and stick form. This is what it looks like here. And if it's written like this, it kind of helps you recognize that there's 2 groups of these NH2 on the carbon oxide double bond. All right. We also want to become familiar with what we call hydrates. Sometimes chemicals absorb water, specifically salts. Salts like to absorb water. Have you ever lived in Hawaii?
Yes, I do live in Hawaii.
That's right. In Hawaii, they put something in the salt shakers. Do you remember what they put in the salt shakers?
No, I don't know what they put in the salt. Just salt?
No. They put something else in the salt shaker.
I don't know.
Well, if you look at the salt shakers on the restaurants or anywhere you go, you'll see a little bit of rice.
Oh, yeah. I know. Yeah, they have the rice in the salt shakers.
Do you know why they put this rice there?
I don't know.
Well, the rice helps absorb the water, because if you don't have the rice, the salt will absorb the water, and when you try to pour it, it'll get stuck in the container. Okay?
Oh, okay.
Yeah, so that property of a chemical to absorb salt or absorb water from the atmosphere is called hygroscopic. And a lot of salts are hygroscopic, and this becomes a little bit of a problem, because if I have a chemical that I want to use in the lab and I need to perform a chemical reaction, and let's say here's my my bottle, right, of this chemical, all right. So I have this bottle, and we can say NaCl, right, whatever the chemical is, it's going to say on the side there. If I had that bottle and I have a lid, the lid helps prevent water from kind of sneaking in and absorbing to the sodium chloride, okay. If I have that bottle and that water, all right, then when I open the lid, the water molecules in the air, right, the water molecules in the air, they're going to sneak in here, and they're going to attach to the surface of the sodium chloride. And you might have seen this when you're cooking, or if you've ever dealt with any materials that are hygroscopic, you open them up, maybe you kept them in the garage, and later on you come to them and you open it, and it's all wet inside, right? That can happen, and then it's kind of ruined your material, right? It's ruined your material. And because some compounds are very hygroscopic, they'll absorb water even if you just leave the cap open for a little bit, then what happens is the material no longer is sodium chloride. Now it's sodium chloride with a little bit of water, for example, right? Or whatever the compound is with a little bit of water. And that becomes a problem, because when you weigh out material here, you have to know exactly what material you're weighing out. You don't want to weigh out some sodium chloride today, but tomorrow weigh out some sodium chloride with a little bit of water, because the mass that you weigh out will not be the sodium chloride. It'll contain what?
Water. Water molecules will be with it.
That's right. Water molecules will be with it. So what we do is we store chemicals hydrated. And that way they don't absorb as much water, and you know exactly what they are. They're always going to be whatever chemical with a given, what we call hydration level, or amount of water molecules, the number of water molecules on that compound. Okay, so this is compound. It's called copper sulfate, and we'll talk about how to name that compound in the future. But copper sulfate here comes with, or the hydrate of copper sulfate, this specific one, comes with 5 water molecules for every unit of that copper sulfate. Okay. Now this becomes confusing if I look at this whole thing as one unit, and I say, how many oxygen atoms are in one of these units? What would you say?
Now, do you mean in copper sulfate?
Well, that's a good question to start off with. How many oxygen atoms are in copper sulfate?
Just in the copper sulfate, there's 4.
That's right, there's 4 in here. Now, if I have 5 water molecules, how many more do I have?
That's 5 more. So 9 altogether if that whole thing is one unit.
That's right, and it is. That's the way you treat it. It's one unit. So we call this thing copper sulfate penta, because penta is the prefix for 5, pentahydrate. Now the dot there is to remind us that the water molecules aren't actually forming a new compound. They're just kind of collecting around the copper sulfate. Okay? So we got copper sulfate pentahydrate. And hydrates, you can heat them, and then you can end up with the dehydrated or anhydrous form of the compound, which would just be copper sulfate by itself. So here's a question. How many units of oxygen then are in 1 unit of copper sulfate?
9.
That's right, 9. Now, sometimes, and this is something that you often see in kind of quiz questions, right? You'll see something like this. 3 iron, hydroxides, hexahydrate. All right, so there it is. This compound is called iron hydroxide, hexahydrate. Okay, and the question might be, how many oxygen atoms are in one unit? Sorry, in this expression. They don't say one unit; they say this expression. So this 3 in front, that is a coefficient, what we call a coefficient, and it's telling me not just 3 of these, or not just 3 irons, it's saying 3 of everything. Like if I were to say 2 sodium chlorides, that means 2 sodium chlorides. It doesn't mean all of a sudden 2 sodiums and 1 chlorine, right? That 2 is telling me 2 of all of this. So if I have this sort of a statement, 3 of these, then we have a tricky question. How many oxygens are there in 3 of those? Okay.
Are you asking me?
Yeah. Can you help us out? Can you do that one?
Well, there's 6 oxygens in from the 6 waters. That 2 down there on the hydroxide,
This one here?
yeah, that is saying that there's 2 oxygens for every iron oxide. So that would be 8 for every unit. And if there's 3, 8 times 3, that's 8 times 3, that's 24. 24 oxygen atoms for the 3 units of iron hydroxide hexahydrate.
That's right. 24 oxygen atoms, right? Again, because there's 2 here, plus the 6 from here, so that's 8, right? And then 8 times the 3 is 24. Now, how about the hydrogen atoms? How many hydrogen atoms?
Well, there's 14 without the 3. So there's 12 down there.
This here, the 12 there.
Yeah, that's right.
Okay, and then then what else?
Well, there's 2 over here.
That's right, over there. That's right, good.
And that's 14 altogether. So then you have 3 times 14. 3 times 14, that's 30, 4 times 3, 12, 46.
14 times 3, is that 46?
I think so. No. 42.
42, right? 4 times 3 is 12. 1 times 3 is 3, so 42. 14 times 3 is 42. Okay, very good. So, now, let's look at this. Can you tell me how many atoms of the different elements, sodium, carbon, and oxygen, there are?
Yeah. 2 sodium, 1 carbon, and 3 oxygen.
Very good. Excellent job. How about this one? This is ammonium sulfate, kind of complex. That 2 there, do you know what that 2 there means?
Yeah, that means that there's 2 of those NH4s.
Yeah, that NH4 is called ammonium. Ammonium. Okay, ammonium. So if there's 2 of these NH4s, 1 of these SO4s, how many nitrogens does that mean we have? 2. That's right, 2 nitrogens. And how many hydrogens?
8.
That's right. And how many sulfurs?
1.
And how many oxygens?
4.
That's right. Very good. 2, 8, 1, and 4. How about magnesium phosphate? Magnesium phosphate. How many magnesiums?
3.
Phosphorus?
2.
And oxygen?
8.
That's right. Very good. This compound here, do you remember its name?
Copper sulfate pentahydrate.
That's right. Copper sulfate pentahydrate. Copper sulfate pentahydrate.
And there's 1 copper, 1 sulfur, 9 oxygen, and 10 hydrogens.
Very good. Excellent job. Very good. Now remember, that 5 there is just for the water molecule. It means that there's 5 what?
Water molecules for every unit of the CuSO4. What's the CuSO4?
Copper sulfate. Copper sulfate. Yeah, it's 5 molecules of water for every copper sulfate. All right. Fabulous job. Now, we're going to talk about the different classifications of matter. Different classifications of matter. Okay? Matter can be separated into what we call pure substances or mixtures. Okay. Now, if it's a pure substance, that means it contains, it is either elemental, all right? So, for example, you could have gold, just a piece of gold, that's elemental, or a piece of diamond or carbon or iron, right? These are all elements that are on our periodic table, right? Okay. Or it could be just a pure substance, like if it's water. Water is an example of a pure substance. Now, when we say pure, that doesn't mean that every atom is the same kind of atom, right? So water is an example of a pure substance. Sodium chloride is an example of a pure substance. Iron phosphate, iron hydroxide, any chemical, as long as everything in that container or your whatever it is you're looking at is the exact same kind of chemical, will be a pure substance. Okay? So, pure substances can be separated into elements or compounds. Elements, all of the material is the same kind of element, whereas compounds, you have different kinds of elements that come together to form these different kinds of compounds. Okay, very good. Now, mixtures. Mixtures are when you have multiple compounds that come together to form not just one kind of material, but something like milk, right, or something like peanut butter, right? Salad dressing is a good example of a mixture. You know, the main components in salad dressing, you have a lot of stuff. What kinds of stuff do you think you would read on the back of a salad dressing ingredients container?
Sugar, salt, water, fat, oil, vinegar.
That's right. Lots of different things like that. Therefore, we know that it's a mixture of lots of different chemicals. Okay? In milk, do you know what the main component in milk is?
Yeah, calcium.
No, calcium. There's some calcium in it. Yeah, it's great. It's a good source of calcium. But the thing that there's the most of, any idea?
Protein?
There's protein in there as well. Very good. Also protein. And that tells us right there, because we know there's calcium and protein, it's got to be a mixture. But there's also fat. There's a lot of other things in milk, right? But the main component is water.
Oh yeah, water. It's mostly water.
That's right. Have you ever milked a cow?
Yes, I used to live on a farm in Idaho, and I would milk cows.
Yeah. Did you use the machines?
Yeah, we would use the machines, but we had a display, a demonstration. People would come by and we'd show them.
Yeah, that's good. Yeah. And when you do milk the cow, what do you get?
Well, you get a bucket full of mostly the watery stuff with a lot of cream on top.
That's right. That's right. So you know that milk is a mixture. And what did you have to do if you wanted that milk? I mean, did you ever drink milk like that?
Yeah, but it was gross.
Okay. But so what did you have to do to make it so you'd want to drink it?
You had to cool it down, and you had to mix it really good.
That's right. There's a fancy word for that mixing. Do you know what it is?
I don't know.
It's called homogenization.
Oh yeah, I knew that.
Yeah, homogenization, which means to make the mixture homogeneous. It's the same throughout, the same amount of the different materials throughout. And that's what homogeneous means, or a homogeneous mixture is a mixture where throughout the whole mixture, everything has the same concentration. Okay? These red and blue dots right here, do you know what that's representing?
No.
That is supposed to be showing us what air is like. Air. Okay? Air is a mixture. Do you know what's in air?
Yeah, there's oxygen and carbon dioxide.
Okay, oxygen and carbon dioxide. Good, but neither of those two things are what's in the highest concentration. Do you know what's in the highest concentration?
Nitrogen?
Yes, nitrogen. That's right. Nitrogen is in the air also. How did you know that?
Well, I can't remember. I think I remember from chemistry class last time.
All right, so nitrogen or air is a mixture. It's a mixture of nitrogen, oxygen, and carbon dioxide.
Oh, I know where I knew that.
Oh, where?
I went to a scuba diving class. I had scuba diving, and I learned that we don't breathe just oxygen gas. That would be too dangerous and probably kill us. You have to have basically compressed air.
That's right. That's right. You need to breathe nitrogen well, you need to breathe oxygen at about 20% oxygen, because that's what the air is out here. Air is 20% oxygen and about 80% nitrogen. That's right, that's right. The rest is basically nitrogen. Okay, so we have mixtures, homogeneous and heterogeneous. Air is an example of a heterogeneous mixture because if you breathe the air at the top of the ceiling or at the bottom of the ceiling, it's going to have basically the same amount of the different components. Okay? Now, we don't want to get confused into thinking, for example, that a compound like this one here is an example of a compound. Iron chloride is its name. We don't want to get into confused in thinking that iron chloride is a mixture. Yes, you could say I mixed iron and chlorine together to make iron chloride, but that's not what our definition of a mixture. Iron chloride, would it be, if it's not a mixture, it has to be a pure substance. Would it be a compound or an element? Compound. That's right, it's a compound. It's a compound because it contains more than one kind of element, right? Let's go back. Do you know if it's an ionic compound or a molecular compound? I can't remember. What did ionic metal? Metal. Oh yeah, that's right. Right, metals. So, is it ionic? That's right. It's an ionic compound. Ionic compound because it contains what?
An iron atom. It's a metal.
Very good. That's right. Okay, excellent. Now let's think about some of these different things down here. What do you think soda is?
A mixture.
That's right. It's a mixture. Syrup?
A mixture.
What's the main component in soda?
Water.
That's right, water. And what was it in milk?
Water.
That's right. And in syrup?
Water.
That's right. We don't drink much else other than water. Everything we drink is basically water. You might drink alcohol, for example.
Never touch the stuff.
What's that?
I don't drink alcohol.
Well, okay, yeah, that's fine. But I mean, in general, people who drink alcohol, ethanol is something that they might drink. And sometimes people just drink straight ethanol. That's usually what vodka is, right? But in general, almost everything we drink is a mixture with water in it. And all of these, which ones would you say are homogeneous and which ones would you say heterogeneous?
Well, the soda is easy. That's homogeneous. And the syrup also, it's homogeneous. Even though the syrup is thicker, it's still homogeneous. The salad dressing is heterogeneous because there's two layers. There's two layers.
That's right, heterogeneous. Now, what about the milk? What would you say about the milk?
Well, the milk's kind of hard. I don't know. What would you call it? Because you have to stir it to make it homogeneous. So right now it's homogeneous, right? But I know that if you leave that, it can separate again.
It can separate. That's right. Yeah. It can separate even if you had it in the store for a while. It can separate again. So that's a good point. And we actually have another word for solutions that are homogenized but will turn heterogeneous if they're left for a long enough time. And that's this word down here.
Suspension?
Yeah, suspension. So milk is a suspension? That's right. Milk is a suspension.
Okay.
All right. So let's take a look at this chart and see what we can learn by showing, or see if we can show what we've learned so far in terms of either a chemical being a pure substance, element, compound, molecule, mixture, heterogeneous, or homogeneous. Okay, let's talk about hot cocoa. So what do you think?
What is hot cocoa?
Oh, you mean like hot chocolate, drinking?
Oh, yeah, okay. Well, it's water. It has water in it, so it's definitely not a pure substance because it has lots of other stuff. So it's got to be a mixture. And I guess it would be, if you had marshmallows, heterogeneous, otherwise homogeneous. Okay, good, fair enough. It probably, could be argued either way, homogeneous or heterogeneous, depending on how it is. How about ice? Ice is just water, right? Yeah, that's right, it's just water. So it would be a pure substance. Element. It's not just an element because it has more than one element. Molecule. What's a molecule again?
Molecule is a compound that only contains nonmetals.
Oh yeah. So, can you bring up the periodic table?
Sure. Let's look at the periodic table.
Hydrogen was an exception. It's a nonmetal, and oxygen's a nonmetal. So, that must be a molecule.
That's right. Water is a molecule and a compound. Or sorry, I gave that one away, didn't I?
Yeah. So it's a pure substance, a molecule, and molecules are also a kind of compound.
That's right. Very good. Excellent. White flour. What do you get, or what would you say white flour is?
I don't know much about flour.
You know how we make flour? How flour is made?
Yeah, I guess so.
What do you have to do to make flour?
You just grind wheat?
That's close enough, right? And when you do grind wheat, what is wheat?
Wheat is something. Wheat is alive. It's a thing, right? So you can't just. It has a lot of stuff. If you plant it, it has DNA. It has protein. That's right. It's a living organism. So if you grind it up, it's like grinding up a person. It's like, shh, that's bad. Don't say that. I know. But I mean, you can't be confused about what wheat is. It's a living system. It has DNA, protein, all sorts of sugars, fats, salts, right? So it's definitely not going to be a pure substance. It's not going to be elemental, compound, molecular. So it's got to be a mixture. And I think that white flour, the white kind we buy at the store, we would pretty much say it's what? Homogeneous.
Yeah, homogeneous. It's basically all the same thing. How about sodium chloride? What would we say sodium chloride is?
It's an ionic compound, so it's going to be compound.
How did you know it's an ionic compound?
Because it has a metal.
It does?
Yeah, sodium, right there, number 11.
Okay, yeah, right. You're correct. Sodium is a metal and chlorine is a nonmetal, so it's an ionic compound. An ionic compound. So it's a ionic compound. Is it an element?
Why not?
Why not?
Because it has two different kinds of elements. It's a compound.
Okay, so it's not an element. Is it a pure substance?
Yes, it can be a pure substance.
That's right, it can be a pure substance because all of the units are sodium chloride in that substance. Is it a mixture?
No, just because you mix the sodium and the chlorine doesn't make it a mixture.
That's right. Very good. So somebody mixed sodium chloride to make the sodium chloride, but that's not our definition of a mixture. Okay, very good. Now I'm going to talk about some of these laws of conservation of mass. First laws of chemistry. The first one is conservation of mass, and then we're going to talk about the law of definite proportions. Okay? So the law of conservation of mass should be pretty straightforward. Basically, whatever you put into the material together, you get out in the products of a chemical reaction. And this is in terms of mass. Matter is never created or destroyed. And that's always true. That's always true. We don't always understand it, and sometimes we get confused. Even nowadays, some people start to say, wait a second, that tree must have come from somewhere else because there was nothing there to start with, and then all of a sudden there's this huge thing there. Right? Trees are made from carbon dioxide, right, in the water. When you burn a tree, it doesn't disappear. It goes back into the carbon as the carbon dioxide. So we don't lose mass when we perform chemical reactions. Sometimes we don't know where it went. It goes off in the terms of gases or whatever, but we never gain or lose mass in chemistry class. Okay? So here's an example. If I have a chemical magnesium, and I burn it in the presence of oxygen to form magnesium oxide, okay? MgO, that's our magnesium oxide. If I know that 16.88 grams of magnesium are consumed and 28.0 grams of magnesium are produced, what mass of oxygen was consumed? How are you going to solve this one?
You just need to subtract them.
Subtract what?
Well, 28 grams of magnesium oxide, and you started with 16.88 grams of magnesium, and you must have mixed some oxygen, so you can tell how much oxygen by subtracting the magnesium oxide, or subtracting the magnesium from the magnesium oxide. Okay, that's right. So if I can write it in terms of a chemical equation,
I have magnesium plus my oxygen atoms coming together to form magnesium oxide. There's 28 grams of this material, 16.88 here. So 28 minus my 16.88, and that's going to be our mass of oxygen. Okay, very good. Now, there's a law of what we call definite proportions, law of definite proportions. And this essentially means that if I mix two chemicals together, so like here I'm mixing magnesium and oxygen, if I mix them together in the same way, I do it here or do it in Europe or do it over in my basement or wherever, then I'm always going to get the same compounds in the same way. Now, if I do it slightly different here than my basement or somewhere else, I can get something different. They can come together in different ways. But in general, if I have the same chemical, if it's magnesium oxide here or magnesium oxide in France, it's going to have the same chemical formula and have the same ratio of magnesiums to oxygens. Okay? So, that is the law of definite proportions. And from that sort of a law, we can answer this kind of a question. In a sample of magnesium oxide that has 16.89 grams of magnesium and 11.11 grams of oxygen, what mass of oxygen would there be in a sample that contains 2 grams of magnesium? So essentially in this question, we have a mass of material, right? And we have another mass of the same material, but it's just a smaller amount, right? So we can tell how much, and the question is, what mass of oxygen would be here, right? How many grams of oxygen? We can tell how many grams of oxygen. This says it has 2 grams of magnesium in the smaller one. How about this one over here? How many grams of magnesium are here? 16.89. That's right, 16.89 grams of magnesium. And then 11.11 what? Grams of oxygen. That's right, grams of oxygen. Okay, so how can I determine the grams of oxygen in that sample over there? You could just use a ratio because it has to be the same ratio. So 16.89 over the 11.11 should be equal to x over the 2. Okay, very good. So if I take my, see if I can find a better pen here. I don't see one. Oh, this one's dead. Okay, so if I take my 16.89, oops, there we go. If I take my 16.89, get a good space here, and I put it over the what? 11.11. 11.11 grams, right? Because this is the grams of magnesium, and this is the grams of oxygen. I can set that equal to what? You can set that equal to, we don't know how much magnesium, so x grams of magnesium over the 2 grams of oxygen. Okay, very good. And how do we solve that? Multiply 16.89 times 2 and then divide by 11. That's right. 16.89 times 2. Oh no, wait, I did that wrong, didn't we? What? We didn't know the grams of oxygen. It said we had 2 grams of magnesium. Oh, yeah. Okay. So you just take the 2 times 11.11 divided by the 16.89. That's right. Very good. And that tells us that answer would be the resulting grams of oxygen. Right. Okay. Very good. The reason we can do that sort of a question is because of the law of definite proportions. We have the same sample of magnesium oxide in both of these trays, and so the ratio of the materials has to be the same. All right. Okay, very good. Now, Charles Dalton was a chemist, or not chemist, but a scientist early on who, he was definitely considered a chemist, but he was also many things. So he was, early on, who identified a theory, or put forth a theory about atoms, right? And his basic theory was that atoms are the smallest unit, the tiniest particle that exists, and that everything is made up of atoms. And that is true. That is true. And his model of the atom had limitations. His model of the atom had limitations, and we'll talk about them later. But in general, he gave us this idea that everything is made up of atoms, something that we take as kind of granted at this point. And then elements can also come together in different ratios, like we said. And this is an example of how sulfur and oxygen come together. Sulfur can come together with 2 oxygens, or sulfur can come together with 3 oxygens. And you can form what's called sulfur dioxide, or you can form sulfur trioxide. And this is called the law of multiple proportions. And essentially what it allows us to do is allows us to recognize that sometimes chemicals come together in different ratios. All right, let's talk briefly then also about our chemical equations. Chemical equations, again, you're probably familiar with this sort of a thing. You have on the left reactants, and on the right of our arrow products. The arrow means like the reaction proceeds to form or yields, something like that. We have our states of matter, solid, liquid, gas. Very good.
What does AQ mean?
Oh, AQ. Yes, AQ stands for aqueous.
Oh yeah, I remember that. Aqueous means it's dissolved in water.
That's right. So it's not really its own phase or anything, its own state, but it is dissolved in water. And a lot of chemistry occurs in water, so we'll see a lot of that in the future. Now, equations don't create atoms. Yeah, don't create atoms or elements. So reactions don't form new elements, or new elements aren't destroyed. So in a chemical reaction, you have to have the same number of the different elements on the left side of the reaction as you do on the right side. And we want to balance the equation, express an equation as a balanced reaction. All we can do to change the number of elements on the left or the right is to change these, what we call coefficients. Now, in front of all of these coefficients, in front of all these elements, the compounds, the element is just, or the coefficient is just 1. All right? This is the only one where there's 2. So let's look at an example. Look at an example. If I have H2O, and I'm going to form H2O by combining hydrogen gas and oxygen gas to form water, right? Is that reaction balanced?
Yeah.
Are you sure? Look closely at that.
Oh, no, it's not. There's 2 hydrogen on the left and 2 on the right, but there's only 1 oxygen atom on the right.
That's right. We have 2 oxygen atoms here. So how can we fix that?
Can you put a 2 at the bottom of that oxygen?
You mean here?
No, down there at the bottom to the right.
Right here?
Yeah.
No, I can't do that, because if I do that, then it's saying that the units here are H2O2, whereas I want to show that this is water, H2O. So I can't do that. I have to put a 2 here. Right? Now when I put a 2 there, how many oxygen atoms are there?
There's 2 on the right and 2 on the left. But you have more hydrogens now.
That's right. I have how many on the right? 4. 4 hydrogens on the right. So what can I do to fix that?
I guess you got to put a 2 in front of the first hydrogen.
That's right. Very good. That's what I have to do. So that's an example of how we balance equations. We have to count the elements that are on the right side or the left side of the equation, and then from that we can use our coefficients to balance the equation. All right, very good. So here's an example. Let's see if we can balance this equation. C8H18O2 yielding, coming together to yield carbon dioxide and water. Have you heard of carbon dioxide before?
Yeah, I know what carbon dioxide is.
Okay, good. A lot of students do know what carbon dioxide is to start off. All right, so when we're going to balance this, I'm just going to write this down here. And so we can work on this piece of paper. Okay, so we got C8H18 plus O2 yielding carbon dioxide and water. All right, so you need more water. What? You need more water. What? Well, how do you know that? Because I have 18 hydrogen on the left and I only have 2 on the right. So you need to put a 9 in front of the water. Like right here? Yeah. Okay, good. So now that gives me 9 times 2, 18 hydrogens, and 18 hydrogens over here. Very good. How many carbons do I need? 8. So what do I have to do? We have to put an 8 in front of the carbon dioxide. That's right, 8 in front of the carbon dioxide. Very good. So am I done? Yeah. Well, wait. Oxygen. No, we need more oxygen on the left. Right now we have 16 plus 9. That's an odd number, though. I don't know how to fix that. 16 plus 9 is 25. What if I put like a 12.5? Isn't 12.5 half of 25? Yeah, but can you do that? Well, you're right. We don't want to have half numbers in there, right? So, but I can do that temporarily. And if I do that temporarily, basically what I'm doing here is I'm saying, okay, this is a balanced scenario. It's not quite finished because we want whole numbers as our coefficients. But now to make 12.5 a whole number, I just multiply it by 2. So now I can make that 2, that what? Oh, 25. Yeah, 25. And then this 16. And then this 18. Very good. So that would be my balanced equation. Okay, do you see how we did that? Yeah, I got it. Okay, good. Very good. So, let's try one more here. Whoa, that's a lot of stuff. Yeah, that's a lot of stuff, isn't it? Let's see if we can do it. I'm going to write down the equation here. This is ammonium NH4 phosphate, PO4, plus barium acetate, C2H3O2, 2. Okay, and then barium phosphate. You know what you do with the dead chemist? What? You bury it. That's funny. Yeah, you bury it, right? All right, and then ammonium phosphate, NH4, C2H3O2. Okay, so move this out of the way, and let's balance this equation. Let me get it up a little bit higher. Very good. Okay, this is an O2 then. Okay. What we were going to do here is we're going to count the different elements. We're going to count the nitrogens, we're going to count the hydrogens, we're going to count the phosphoruses, the bariums, carbons, hydrogens, and oxygens. And then we're going to make sure we have the same amount on both sides, right? But I'm going to show you a little trick here because it becomes simpler if we recognize that the different elements come in different groups. So for example, NH4. Do you see that group over there to the right of the equation at all? Yeah, I see that. So there's 3 of them here, and how many of them over here? 1. That's right. So what can we do to fix that? Put a 3 over there. That's right. So if I put a 3 here, like that, now I have 3 of these NH4 are called ammoniums, and 3 over here. Very good. So what does that mean? Wait a second. That gives me 3 of the C2H3O2s over there, and you have 2 over on the left. That's right. So what are we going to do there? Well, you're going to have to make one of those a 6, right? Like put a 6 over there and a 3 in front of the Ba, the barium. So if I put a 3 here and a 6 there, yeah, because that'll give you 6 acetates, and then you're going to have to put a 6 in front of the NH4. 6 here? I think so. 6 there? Yeah, 6 NH4, 6 NH4, 6 acetates, 6 C2H3O2s, 6 C2H3O2s on the left. How about bariums? How are they? Got 3 over there, 3 over here. How about the phosphates? Are they okay?
Oh, wait, no, this doesn't have to be a 6. You don't want that to be a 6.
Which one? This one here?
No, over here.
Or this one here?
Yeah, that has to be only a 2 because you already have 3 there.
Okay, very good. 2. So now we have 6 here. 2 phosphates. And does that work with the phosphates?
Yeah, I think we're done. I think we're done.
Okay, good job. Let's see if that is our answer. Very good. 2, 3, 1, 6. Very good. Excellent job. So, that was chapter 1. Job well done. I hope you learned a little bit, or maybe reviewed a little bit, and we're learning. Good job. See you next time.
Okay, bye.